Wonderful. So we're carrying on with what is objectively the best element on the table. Certainly my favorite element. Right. So Simon was talking specifically about this red clump lithium problem, which is, given how long we've spent looking at lithium in giant stars, amazing that there's a brand new thing sitting right there that we hadn't noticed before. And I'm very excited to see what he does with that, what we can all do to figure that all out. What I want to talk about is a recent paper that takes a slightly broader view, which has the title A Census of Lithium-Rich Giant Stars, which is work that I did in the last couple of years with Aditya and Jeffrey and Sanjeev and the rest of the GALAH team. So yeah, the central question is exactly what Simon said, that it's easy to destroy lithium in the universe. It's hard to make it in stars, but there are sort of 1% of stars that have far more lithium than they ought to. And so we've always been trying to figure out, since the first one of these was found completely by accident, why is this happening? Like, this should not happen. And so the beginning of this will be very similar to the beginning of Simon's talk. We have been trying to look at the overall properties of the data set to understand what might be making these stars different to the rest of giant stars, right? And so we look at where they are in evolutionary phase, and we see that indeed a lot of them are near the red clump or on the giant branch. I would point out that there are quite a lot of stars up here that didn't get much play in the previous talk, but they are not the majority of the sample, right? Early on in the study of this, it was hotly debated whether these were actually core helium burning stars or whether they were stars at the RGB bump or earlier in red giant evolution. But seismology has completely changed the way that we look at these stars. It has made it really clear what they are. So there have been a lot of mechanisms suggested as the possible source of all of this lithium. The one that Simon is talking about is that maybe this happens in all stars and we just hadn't noticed before. It's also being suggested that maybe an internal mixing process could take lithium that's being produced in a hot region of the star and convect it up to the cooler regions of the stars very quickly. There are a couple of different possibilities listed in this very handy diagram from Andy Casey. There's also just rotationally induced mixing, which is effective and mysterious and can be responsible for a lot of things in stellar abundances. So there are a lot of models out there. There's a huge amount of literature on this topic. That is all I'm going to say about it, which is really unfair to everybody who's done all of that work. But it's a 10-minute talk. So one of the problems in dealing with this is that lithium-rich giants are otherwise not special, right? They're sort of 1% of the overall population, but there's nothing else about them that is easier to observe than the lithium abundance that would tell you about the lithium abundance. So they're not cooler or more luminous or, somehow different to ordinary red giant stars. And so even in samples in the Sloan Digital Sky Survey or in Gaia ESO, when you get together a sample to write a paper on this, you get about 25 new lithium-rich stars. And that's just not enough to really sample the parameter space to really get a handle on every different mechanism that has been suggested and whether it's a reasonable explanation. And so actually it's LAMAST and astroseismology that have really changed the way that we see this field. So Hongliang Yan in LAMAST has been doing an amazing job of taking their giant data set and producing big catalogs. Andy Casey and Anna Ho also did a big project with LAMAST that turned up 2,000 new lithium-rich giants, which is an amazing, like what we can do with that is so much bigger than what we could do with 25 stars, right? And so we've really been able to, there's been a lot of developments in this in just the last couple of years, which is very exciting. So our goal with this was to say, well, in GALAH, we get the lithium line, we have that in our data set, it's right there. And so we might as well look at those abundances and see what we can do with this. As it turns out, and this is sort of a thing that Evan was alluding to earlier, and you can see it in the spectrum as well, not every star that we observe in GALAH will have a measurable lithium abundance. And so the red spectrum is one that clearly has a nice strong lithium abundance, but the rest of them, all of the other gray spectra that are very similar in stellar parameters, but not enhanced in lithium, there's no real line there. And so we don't have a measured abundance for every single star, but we are confident in the ones that we do have. So the plot on the right is color magnitude and Kiel diagrams for all of GALAH in the background. And then on the lower panels, the lithium-rich and super lithium-rich stars are highlighted in red and black. And so you can see that they do, if you don't think about the selection function too hard, even without worrying about that, you can see that they do tend to be red clump stars. And there are also red giant stars in that mix. And so we took this data set and then we started looking at what can we tell from a data set like this? What can we learn from it? So one of the things you can look at is the occurrence rate of lithium richness, right? So the fraction of stars that have high lithium abundance, which is the bottom panel of both of these things. And we've split it up into red clump stars on the left, RGB stars on the right. And what we find is that the red clump stars, the probability that they'll be lithium rich rises as the metallicity goes up, which will tell us something about the lithium enrichment process being more permitted at higher metallicity or more restricted at low metallicity. But interestingly, the red giants are very different. The probability on that is low, less than 1% for almost all of them. And then right at 0, the probability shoots up. And so this says that the process, whatever it may be, could be different between the two, but it's more restricted in red giants and less restricted in red clump stars. And so Simon's model of everything becomes at least a little bit lithium rich at the helium flash brings a really interesting sort of lens onto this, that, you know, that's something that's happening to potentially all of the red clump stars. And there's an entirely different thing that's possibly happening to all of to some fraction of the red giant red stars that is in some way sensitive to metallicity. And that this figure was intended as a comparison to one that Andy Casey did a couple of years before out of Lamast, where this is all the stars together. And you see a increase in the probability that a star will be lithium rich as the metallicity goes up. But what we were able to do is to separate it into those two evolutionary phases and to see that they actually behave differently. Another thing we were able to do is to divide the primary red clump and the secondary red clump, which is really a mass separation. So the primary red clump are all below about 2.5 solar masses, and the secondary are higher mass than that. They don't actually have a helium flash per se because they're more massive and can just begin helium fusion directly. And so their distribution in lithium abundance space is somewhat different. So this plot, now the red clump stars are on the top, the red giant branch stars are on the bottom, and the x-axes are temperature, log G, and metallicity. So there's a lot going on here. Huh?
2 minutes.
Oh, cool. Yeah, okay. But one thing to point out is that the secondary red clump stars don't tend to be lithium enhanced as often as the primary ones do, which again maybe says something about whether the helium flash is responsible. One of the things to point out is we definitely have a sensitivity limit where hot stars would be harder for us to, but you need a higher lithium abundance for us to be able to confidently measure it as the temperature goes up, which is fine. And this goes with one of Jan's papers, which was about the most lithium-rich star they found in Lamast, which is up here at sort of 4.8. In our sample, we cut off around 4.2 because the lines get really strong. And ironically there, you also want to be a little bit careful that your interpretation is correct. But we can definitely confirm that stars get that lithium rich in our set as well as in their one star that they found. Although we cannot tell you why at this point. And then the other thing that I want to say is that in the next paper that they had in 2020, they in their data set found that they didn't have any giant branch stars more lithium rich than about 2.5. And that is not something we produce in our data set. We find red giant branch stars sort of going all the way up to the top of our sensitivity range. So there is something different in the way our two data sets are constructed. And it would be interesting to look at why we see different snapshots of the RGB lithium-rich population. Finally, one of the suggestions for lithium production has been rapid rotation, rotationally induced mixing. This is a thing that is hard to prove or disprove because red giants don't tend to rotate very fast. But we do see some connection between rotation and lithium richness. So not all lithium-rich stars are going to be rapid rotators, but on the red clump, if they are rapid rotators out on the right side of this plot, they're more likely to be super lithium-rich than regular lithium-rich, for whatever that means. So we're a little unclear on what exactly all this means. Unfortunately, we can't say anything about binarity from the data set that we have because GALAH does not do a lot of cadence in time. Hopefully, as the TESS rotation curve stuff comes along, we'll be able to put these things together and say something more about the rotation speeds of our stars. And so, yeah, I think my goal coming up is very similar to Simon's, in that we have now a data set that really samples this whole parameter space of evolutionary phase and metallicity and level of lithium enrichment. And we'd like to start testing all of these things that have been suggested. And so Jeffrey and one of our students are working on a model that will have sort of generically all of these possible mechanisms, and then we'll turn things on and off, and we will see what kind of lithium abundance distribution gets produced and try to work out what are reasonable parameters that could produce the actual data set that we have. So thanks.
All right, thanks, Sarah. Yeah, looking forward to figuring out what happens when you turn or turn off certain of these components.
Yeah, I mean, my take on it is that probably everything is happening at once. And there's not one right answer, but everything that's possible is going to be contributing at some level. Yeah, absolutely. I'm not sure if Rosie's question was for the previous talk, but since the topic is very similar, I might just reuse it or recycle it. Rosie was wondering if there's blue horizontal branch stars that are lithium rich in general, but possibly also for this particular data set. I don't know. No, they're hot enough that we would have a hard time with that.
Yeah, we don't have very many good cluster stars in GALAH, and yeah, they're way too hot in GALAH.
Yeah. So I don't know that our analysis could capture that. The lithium might be all ionized. It would be hard to tell. Evan, do you know?
Nope.
All right. Do we have more questions for Sarah?
Dan's got his hand up.
Oh yeah, Dan, go for it.
Okay, very naive question. So if you've got higher rotational rate, and I realize it wasn't like a strong trend or anything, but that higher rotational rate, wouldn't that, again, naively increase mixing, which might increase the destruction? Absolutely.
And yet, at least on the red clump, the ones that rotate faster have more lithium.
And yet they move.
Exactly.
All right, good. Yeah, I think so. Simon also agreed that for the BHB stars, the lithium lines would most likely be undetectable due to the high temperatures. All right. Well, I don't see any other. Oh, I think. Wait, Dennis in the back.
So Tim
yes.
And Dennis both have questions.
All right, Dennis is in the back, I assume. So Dennis, go for it.
So have you looked at any Gaia measurements that indicate primarity that you couldn't get
Yeah. So
Sarah, can you just yeah
if you
thanks.
couldn't hear that, the question was, does any of the Gaia astrometry tell you anything about binarity? So the astrometric uncertainty or things like that. And I believe we looked at that, but these stars are far enough away that it would not be very obvious.
Yeah, and also the anti-casing model requires them to have 100-day plus orbits or something. So the wobble isn't big enough.
And also, in case you couldn't hear that either, the predicted orbital periods are quite long. And so it may not, also there may not be enough time baseline in Gaia to really see that.
All right, there is another hand raised, so I think we can just have that one question also. The person.
Reading here.
Oh, hi Tim.
Hi, really silly question. How many hot Jupiters do you have to swallow to push your lithium up to these levels?
One, for normal amount of lithium enrichment, sort of one.
One.
And there are really great models on this by Claudia Aguilar Gomez, and sort of varying all the different parameters and seeing what happens to the lithium abundance over time. Yeah. To get to the really high ones, I don't think that's possible.